Good afternoon and welcome to this afternoon's webinar, How to Extend Lead-Acid Battery Life with Timely Testing. My name is Paul Custer from Transcat, and I'll be your moderator this afternoon. Today, we'd like to welcome Kurt Salou, Chairman, Founder, and Chief Executive Officer of Global Energy Innovations, who will be leading us through the webinar. Just a couple of housekeeping notes. We'll spend the first part of our time in the presentation and end the call with any questions if you have. Anytime you do have questions during the presentation, you can send your questions to the question box to the right in your webinar controls. If we do happen to run out of time before getting to all your questions, we'll be sure to follow up offline to the email that you registered with to provide you with the answer to the question. I did also want to mention that this webinar is being recorded and will be available for viewing through the Transcat YouTube channel, and will also be forwarded to you via email. In addition, we'll make the presentation slides available to you. At this time, I'm going to turn it over to Kurt to lead us through the presentation.
Thank you very much. My name is Kurt Salou. I'm the CEO and one of the founders of Global Energy Innovations. Today I'm going to give you an overview of extending the life of lead-acid batteries, also reducing the cost and risk of battery ownership, and testing in a timely fashion so you can reduce downtime. Okay? And I'm going to be covering several products that we manufacture that Transcat distributes, and going through those products and how they function in the marketplace. Global Energy Innovations, we manufacture very precise battery monitoring, testing, conditioning equipment to restore batteries, and also the enterprise software, Oracle-based with SAP reporting that goes along with it so you can track your assets in a number of different industries. Okay, our products are used in the mobile telecommunication, power generation, which is utility, distribution, power generation, uninterrupted power systems, UPS, and also a host of other battery users, people that use batteries in cycling for solar, off-grid, and on-grid, industrial battery manufacturers, and a host of other battery users. Okay? And I'm going to be going through how our products are used and what's the differentiation technically from the other products that are on the market today. Okay, I thought I'd give a couple slides on the lead-acid battery market. And what I thought I would do is give 5 customers that we work with and give you an idea of their installed base of lead-acid batteries, because the lead-acid battery market has been growing, and it's growing at a very rapid rate with the growth of telecom, with the growth of data centers, and the need for reliable power and uninterrupted power. And I go through the Utah data center. Most of you know that's the one being built for cybersecurity. They've installed roughly $22 million of lead-acid batteries to back up that data center. That data center's is anticipating to be drawing about 260 megawatts of power from the grid, and that's one of the largest battery installation that I've seen. Those are C&D batteries, and they're storing roughly a yottabyte of information at that data center. So uptime is very important at that data center. Testing those batteries, making sure that they're not going to fail in an incident or when their exercise is very important. Telmex is a Latin American carrier owned by Carlos Slim. In Mexico only, they carry roughly 260 million of lead acid, largely flooded, wet cells. And those are used to back up the fiber network, the telecommunication networks for Telmex's sites. Okay? A large U.S. search engine company running several million servers is roughly at $160 million of lead acid install base. Okay, CFE is a utility in Mexico. They are the Mexican power company, and they're carrying roughly $126 million. Northwestern Energy roughly 8. Okay, and these are estimates. So when you look at 5 companies, you're at roughly $500 million of install base of lead acid. If you look at the market today, it's hovering about $5+ billion in replacement per year, with an install base that's in the 55 to 60 billion range. And that number is growing at roughly 5.5 to 6% per year, and the cost of downtime is going up. And that's largely because we live in an era that downtime and communication staying up permanently is becoming a requirement. Okay, so what is the problem that we see out there in the industry? Number one is customers need to replace lead-acid batteries very often. And often these batteries last half or less than half of their life because they're either not properly maintained or they're not properly tested so they can be maintained in a thoughtful fashion. Okay? So the second point is battery systems often fail without notice, and as I mentioned before, the cost of downtime is increasing for really all market segments. Everything from rail to data centers to telecommunication to utilities. As many of you know, in the utility segment, NERC and FERC are highly regulating the utilities. That's distribution, transmission, power generation. At all these locations, batteries are used, lead acid, to pick up the load temporarily, or they're used in dielectric relays to shift power, and those are mission critical. Okay, and with the growing requirements on the grid and demand, the requirement for these systems to work properly is very high, because a fault on the grid can now cause catastrophic problems and domino effects. So NERC and FERC are being very strict in regulating the test requirements are more and more strict. Okay, and most battery testers on the market, and we'll go into this later in the presentation, often do not pick up a battery that's going to fail when it's brought under load. Okay, and what I'm going to be talking about is 2 different categories of test. One we call a lagging indicator, meaning that it picks something up when the battery is already in its replacement zone, and that's voltage and a single point impedance reading. And then we have something called, we termed leading indicators. Okay, and these leading indicators are what our technology does, and these leading indicators allow you to pick up faults or failures or degradation in a lead-acid battery far before it's in its failure zone. Okay, so you can see on the chart on the right here, you install batteries when they're new. The goal is to test them and service them and extend the life of the system before you replace them. And as I mentioned earlier on in this slide, very often batteries are installed. They're either tested improperly or they're not tested at all. They're not serviced properly or they're serviced very little, and consequently they're replaced very early in life. Okay, and we see this very regularly. If you look at North American's telecommunication network with AT&T, Verizon, and other carriers, often batteries will last 5 years when their expected life is 10 to 12, sometimes 15 years. That's a very, very big CapEx cost for these carriers. So knowing how to rapidly test them and service them properly is a very important function for these different companies that carry large install base of lead-acid batteries. Okay. I covered this a little bit earlier in that prior slide. This graph here talks about the different terminologies, the different terms of how we test. Okay, we'll start out with battery voltage. When you test battery voltage, we call this a lagging indicator, because battery voltage often only changes dramatically when you're in the failure zone. Okay, so battery voltage changes as a function of state of charge. In most all battery systems, it's a fairly plateauing charge with a dip at the end. However, as batteries age and they get into their failure zone, they will show a dramatic decline in voltage, and we'll look at some plots of that later. But we only really see that that change as they near their end of life. So we're not going to be able to use that indicator in the middle of life to adjust things to increase the life of that system. And again, that's what we call a lagging indicator. Okay? Single point battery impedance we also consider a lagging indicator. Even though we can see a subtle change, the big change at end of life comes and you see a rapid increase. But if you're testing quarterly or if you're testing biannually, often that battery will be in what we call the failure zone, and it will fail if it goes under load, but it may not have gotten picked up when it was tested. Okay? Now, flooded systems, batteries that are wet, unlike valve-regulated, where they're called starved electrolyte systems, flooded systems have this change, and it's a much more gradual change in the flooded systems, where valve-regulated, which is being used predominantly in the telecom, and it's been a battery configuration that's getting used more and more frequently. That battery chemistry, valve-regulated battery, tends to fail very, very rapidly without a lot of warning. So that's where these leading indicators come into play. So a leading indicator would be something that gives you warning or notice that there's something going wrong, so you can either replace that single battery in a battery string, or you can adjust something, the float voltage, the temperature at the site, to prevent further degradation. And I'll go through these two. One is sulfation, and sulfation is the natural way a battery cycles, meaning that you go from lead to lead sulfate as you charge and discharge a battery. However, if you're not properly charging it or floating it at the right voltage, you can see excessive sulfation that causes the battery system to no longer accept charge effectively. Okay? And that's something that you want to be able to find early in life so you can correct it before it becomes irreversible in the system. Okay? That would be considered a leading indicator. Global Energy handheld products test for that, and you can make proper adjustments to your battery system so that you don't have a system that is no longer healthy and needs to be replaced. Okay? Dry out is another indicator. Dry out applies to valve-regulated systems. They're called starved electrolyte systems. They're sealed. There's a recombination of the hydrogen and the oxygen to go back to water. And they've been termed in the industry as maintenance-free batteries. Thus, they're used quite regularly. They're rack-mounted. You can save space for them. And these battery systems have grown considerably in terms of market size globally, not just in North America. They can have problems over time where some of the electrolyte or the water will leave the system and will have a dry out phenomena which will cause battery failure. Okay? That dry out is only picked up, okay, on a single point impedance after the separator comes off one of the electrodes and you have a catastrophic failure. So it's a very rapid failure mode. In our system, using a multi-frequency approach, you can pick up the beginnings of dry out. You can pick up the beginnings of water leaving that system with electrolyte getting more concentrated. That allows you to either pull that system out or correct it. Now, in a dry out situation, that's typically a faulty valve or an improperly activated cell. Those typically are taken out of the system. Okay? So what does our system do different? What is the value of doing a multi-frequency scan, or what we call a cell scan, chemical electrical layer scan? Okay, this is a plot of a multi-frequency scan. Okay, and if you don't worry about the axes, the bottom, the real, or the imaginary, what we can see is a curve that develops from higher frequencies that are on the left to lower frequencies that are on the right. Okay, and this type of graph has been for many years referred to as electrochemical impedance spectroscopy. So you're putting in a waveform, a sinusoidal waveform, and you're getting a response from any system, not just an electrochemical system. You could do it on a resistor and a capacitor. You'll get a certain response. Okay, and in lead-acid batteries, this response can be monitored, and you can pick up in these curves the different phenomena that are happening. Okay, so let me walk you through this curve. The higher frequencies, you'll pick up things such as series resistances, corrosion on the terminals, sulfation as you move to slightly lower frequencies. And you'll start to be able to piece together the failure modes that are associated with conductive elements. As you go to the lower frequencies, you'll start to pick up electrolyte issues such as dry out. And these can be separated, and the failure modes can be distinguished using classification and pattern recognition on these curves, much like you would voice recognition, where you say hello, my hello spectrum looks very different than someone else's, and I can be identified that way. Same thing goes for the fault modes or the cell scan leading indicators in lead-acid battery failure. Okay, and this is a curve that was recently taken on the black being a very new, freshly activated lead-acid cell, and this on a cell that is cycled 450 times and is no longer healthy and will no longer hold the charge. You can see that in this plot they look very different. You can see if you plot frequency versus total impedance over the multiple points, you get a very different plot. Well, the way the black curve goes to the blue curve is very telling of what's happening with either sulfation or dry out or failure mode in the system. And this curve can be distinguished of whether it's a dry out or a sulfation phenomenon. And that is what a multi-frequency scan will do for you. Okay? This is a summary. And I'll walk you through the summary. Our system puts in a multi-frequency sine wave. Okay, that waveform, the response from that is captured. Okay, from that we can classify the state or fingerprint, I'll call it, the waveform coming back. Okay, and we can use software on the handheld. Okay, we use fast Fourier transforms, we use digital signal processing to receive back that waveform, classify it, and allow the user to know how much capacity they've lost due to this failure mode and what failure mode's predominant. So I always make the analogy that our system is like a CAT scan. A single point reading might be more like an X-ray where you don't get that fine detail of what's happening internally, and that's why a multi-frequency scan is so important if you want to see the leading indicators and what's causing battery failure. Okay? Once that happens, it's served up to the end user as a pass-fail based on how much capacity you've lost in the system. So under the hood, this frequency response analyzer is not showcased on the screen. There's no curves. You don't see these type of curves in the readout. You see a pass-fail, so you can rapidly go through and test your system and pick up the weak cells of the string. Okay? And what I'd like to do now is go through some data that comes off of this handheld analyzer and show you a site that is a real live site out there in the industry. Okay, this is a Northwestern Energy site, and if you look at this site, you'll see you can take a single point reading, and our analyzer does that, much like some of the competitive products, and I'll show you a summary of those products. You can see from the impedance measurement, everything looks in spec, meaning that it looks like it's okay. You do see variations here, okay, of slightly higher impedances, but they still haven't hit their warning mark. So to the untrained eye, this would look like a system that should just be left alone, and you could move on to the next string and test. You can see that you do have a depressed float voltage on this side of the string. Okay, and you can see certainly very heavy sulfation. And you can see on some of these cells we've lost as much as 20% of our capacity due to sulfation. So this is what we would call a string of batteries that's very much out of family and needs to be corrected. Float voltage needs to be corrected. This needs to be equalized. And these preventative maintenance steps would not be taken into consideration from just a single point reading. If you were very trained, you could look at the voltage, separate the string into two parts, equalize it, bring it back to its health. You can do that with the Dynapulse that we sell. But the leading indicator, the sulfation reading, really tells you, okay, it's time to take care of the string or we're going to lose this asset. Okay, and this is very common, not just in utility sites, but in telecommunication, where often you'll have thermal or temperature variations at the site, and the batteries don't age all the same. You get some batteries in the string that age quicker than others due to temperature fluctuations. You might have a bus bar or a strap that's corroded that will cause several cells to fall out of family from a voltage and impedance perspective. So being able to rapidly test these and pick them up is important. Okay, this is another string from a site that I'm not listing. And this one, you can see once again, from the top, you see that the impedances are all in family. Okay, you can see voltages are jumping around quite a bit. You have some depressed voltages here. You've got some lower voltages here. The float voltage on this string should be about 2.25. So you can see some are elevated, some are depressed. The average string voltage is still within specification for that string. So unless you go in and test each one and see this sulfation, you might just adjust float voltage and put the string and walk away from the string, where if you did that, you would see that these cells here either need to be equalized and retested or taken out of the string because you've lost 30%. At roughly 20%, that's where most people say the battery has lost 20% of its nameplate capacity. It's time to replace this battery. So unless you load tested this whole string, you wouldn't know. Okay, so this is a very good instance where getting the leading indicators will help you better maintain the string and keep it healthy over a longer period of time. Okay, back to what our technology does. It really is a frequency response analyzer, a lab-grade frequency response analyzer that's been repackaged to put into your hand that's not an R&D or lab-grade type of tool. It runs algorithms to present the lead-acid parameters. And so it's been a miniaturized, very accurate frequency response analyzer. There aren't any other products out on the market that do that. Some other products that do frequency response that aren't lab-grade equipment are things like the Doble transformer testers, where you can sweep a frequency through a transformer to pick up corrosive elements that are starting to corrode. You can pick up impurities in the dielectrics in those transformers. And you can pick up deformation of the coils if that transformer was damaged on shipment, or if there was an event, a lightning strike, and something changed in that transformer. Frequency response would allow you to pick that up. So what have we done? We've taken lab-grade equipment, miniaturized it, and we've put the knowledge of the electrochemistry, and I put PhD here. It was the analytics and the scientific work of doing the classification on these failure modes. It got put into the handheld so that you have a very rapid test, a go, no-go, fail, pass, and warn for fault modes in lead acid. Okay, so let's take a peek at what else is on the industry. What do these other products do? Okay, and there is some very good overviews on our website. There's a 15-minute video that compares all of the equipment in the marketplace. It shows what they do. It gives a very good overview of what these different analyzers do. I'm going to touch on them very briefly, but if you do want to get a more in-depth overview, you can go to our website. There's a video section where there's a host of videos that talk about the competition, talk about our technology in different industries, how our product is used. Okay, so I'll talk about ours first. Ours does the electrical properties, which I referred to before as the lagging indicators. We still measure voltage. We measure impedance. Some people call the impedance measurement a resistance or a conductance. In the case of Medtronics, they do a conductance reading. Albert does a DC resistance. Okay. Megger does an impedance test, and Hioki does an impedance test as well. What you'll learn from these products, with the exception of Megger, is that these waveforms that they put in are their own proprietary waveform. Okay, they're typically square waves or some type of an adjusted sine wave. Okay, where our product is a true frequency response analyzer, and it puts in a mistraceable sine wave, and it responds just as a lab-grade piece of equipment. When we built our algorithms for these products on lead acid, we did them with lab-grade tools, and we ported those algorithms over to our handheld. So as we improve the algorithms, launch other features and functions on it, as you upgrade the firmware to add additional features in the future, it's all from lab-grade test and measurement equipment. Okay, the other products in the market, like Medtronic, they do a conductance reading. They're doing some type of an excitation, okay, and that excitation they return and they produce a conductance reading, okay. Megger does as close as any of the products to a true impedance reading, okay. Albert, as I mentioned before, it's an interrupt load, and they present the resistance value. Now, one thing to take in mind with the Medtronics and the Albert is that when they do excite the system, they push it out of equilibrium such that each subsequent test there's a voltage skewing effect, meaning the voltage of that battery or system changes as a function of each test. Okay, our system puts in a very, very low amplitude sine wave. It goes through the zero crossing, so the system is undisturbed and unchanged. Okay, many of the systems have enterprise software. Some of these have been upgraded to have oscilloscopes. Ours has an oscilloscope so that you can test the features of, or the state of the rectifiers or chargers that are charging the batteries to see if there's a lot of noise that can affect the battery health. Okay, and there's other features on these products that correct for temperatures. I think more recently Medtronics has added a temperature correction feature. Okay. What I'd like to do is I'm going to go into a few other slides because we have a bit more time, okay, and I will come back to a Q&A section and leave about 15 minutes for Q&A, okay, or maybe about 10 minutes. I think it's 11:30 now, just about 11:30, so I thought I'd go through some supporting slides that would be interesting for the group. Okay, this one I went through before. This one here I thought would be a very interesting piece of data. In the telecommunication market, it's not uncommon for a battery failure to destroy a cabinet or fail catastrophically because often they're not tested more than yearly. If you look at cell towers, this is a report from Battery Power that said 62% of cell tower failures are power-related, 80% of these are battery-related. So it means 50% are related to the batteries. Okay, and I'd like to end with that. I do have a few supportings, but I think it would be good to open it up for questions. We are at the 11:30 mark.
Okay, thanks, Kurt. We've got a couple of questions so far. Again, feel free to type your questions into the question box, and we'll be sure to read those off and get those answered for you. First question, is there critical mass required for an investment in these products? I do not have a large install base.
When you say is there a critical mass, is it possible to hear the person and get a little more feedback on critical mass?
I think they're talking in terms of number of batteries.
Oh, okay. So let me rephrase the question. They're asking, is there a critical mass, meaning would I need so many batteries to be using this type of tool and this type of equipment? Would
Correct.
you say, Paul, that's the question?
Correct,
well,
yes.
You know, we know people that have one off-grid solar site, okay? And I'll actually, in answering this question, just pull up on here an industry and stationary power, where it depends the cost of your system, because some off-grid solar applications, I'll go up here, have $30,000, $40,000 of batteries, and if you don't test them properly and equalize them, you could lose those batteries in the course of several years, where they're supposed to last 10 or 15. So the cost of the tool far outweighs the cost of replacing those batteries, meaning that buying the tool makes a lot of sense. Okay, so if you were to go up to our site, you could see several solar installations where they have enough of, they're small installations, however, they're still costly to replace. So I think the judgment on the equipment is really what is the cost of your install base. It doesn't have to be hundreds of millions of dollars to have several units. It could be as much as one or two strings that you want to make sure last their life.
Okay. Next question is, how often should discharge tests be performed?
That discharge test, it depends on the application. So if you have a telecom or utility flooded battery that is meant to float, okay, for long, long periods, meaning 10, 15 years, then there's been additives to those plates, antimony, calcium, and other things to prevent corrosion, extend their life. Those type of batteries, you want to do the discharge test very infrequently, okay, yearly at maximum, I would say, okay, because each time you do a discharge on, I'll call it a brittle plate, something that's made to run a long time in a float application, you're actually decreasing the life of that system, okay? So if you were to take a battery, like a GNB battery that's meant to cycle, a lead-acid cycle or a marine type of battery, or just a battery that's made to go down to a lower depth of discharge like ones in solar sites, then doing a capacity test on those is really not going to reduce the life, and that could be done much more frequently. So in a lot of utility and power generation, they're doing quarterly or biannual testing with equipment like ours, and they're required often to do a yearly load test where they have to bring a large load and do a complete or 70-odd% discharge, or discharge down to a certain voltage. Now, one thing to take into consideration with that is these discharge tests are not only very lengthy, but they take very large discharge loads, because you can imagine if you have a flooded system that is several thousand amp hours at several hundred volts, that's a very large amount of power that you have to dissipate over, say, an 8-hour rate. So those typically are very costly, and you have to also back that string up while you're doing that test. So to answer the question, back to it, it depends on the battery type and what the use application, how it was made, and then it often depends on what is that cost for actually doing that load test.
Okay. Next question is, when you have a string of, say, 6 batteries, how do you determine which battery is failing?
Did you say if you have a string of 6 batteries?
Right.
Okay, so I'm going to say there's 6 cells or 6 batteries in the string, okay, and you want to know what's happening and then which one is failing. I'll give you an example here. We'll go to this graph here. Let's say that this was just 6 and it wasn't the 60-cell string that it is, okay? Let's say that this was 6. You could take a look at cell 20 here and you could say, this one is probably reaching end of life. It probably has a problem. This would be considered a failed cell, okay? And I will pull up from our database using IBMS. I'll pull up a string that has dry out, and you'll just see one spike. And I'm going to move this off so I won't show the customer name. But I'm going to pull up a string, and I'll show you one that has dry out in it. And that dry out is indicative of a cell that's failed. Okay, so this is the database. I'm going to just pull one up that has it'll have a dry out condition, and that should show us a faulty cell. Well, this is actually, I'll just pull this one up because I'm having a little trouble finding one that dried out right now. Okay, so this is a good indication that we have a number of dried out cells in this string. We have some heavy sulfation here, and impedance is showing that this string is pretty much at end of life. So this would be an indication of a bunch that are bad. But a red indication, okay, out of family, out of the alarm zone that you see here, is indicative of a bad cell in that string that you'd want to either replace or try and recover.
Okay, next question. Can this equipment be used for SLA?
Yes, we starting lighting ignition batteries. Now I'm assuming that that's SLA, not stationary lead acid. So certainly it can be used on stationary lead acid, which is often referred to as SLA. But if the term is starting lighting ignition, SLI, then I'll talk about that. But I think he said SLA. Is that correct?
That's correct.
Okay, so that would be stationary lead acid. And stationary lead acid is really where this product is intended to be used. Okay, that's utility, telecom, backup power. if you went to the industries here on our website, you would see that stationary power is stationary lead acid. You have data centers, grid storage, oil and gas, and you could see that in an oil and gas application, this would be considered stationary lead acid. Okay, so flooded or valve regulated, used for backup power and drill platforms and others, that would all be stationary lead acid. So the answer is yes.
And yes, they did just clarify, and he said sealed lead acid.
Okay, so sealed would be valve regulated, okay, and that's what I was talking about earlier. That's where you'd see a dry out. So a sealed lead acid indicates that the system's sealed. You're not going to add water, do specific gravity type of tests. So in a sealed system, you'd be testing for heavy sulfation, dry out, impedance, voltage. Okay, so yes, you would be using a sealed lead acid battery. Is used in many of these different industries, and it's testable with our product.
Okay. Next question is, what is the ballpark manufacturer list price for a complete test system as shown?
A ballpark price. Well, if you look at Transcat, ours lists for $79.95. That's the handheld. Our continuous monitoring system is due out on the market. We have systems in beta test. We'll be launching pricing on that shortly. I don't have an exact date for that yet. But we will be highly competitive with other stationary continuous monitoring systems that you have on the market. And if you look at our system, the databases are shared, so you can do a handheld or a continuous test, and you can use multiple analyzers or continuous monitoring across one organization and share that data and compare the data.
And looks like one more question. How many handheld units should you have per number of units tested?
It's going to depend on how many batteries you have at those different sites and what the throughput is for your test engineers. We see large telecom and utility companies that we serve having sometimes upwards of 50, 100 units because they have large geographic regions. Some of the utilities that stretch over large regions will have a handheld or several per region. Some organizations have a handheld per operator because they find that not having it in their hand when they hit a site, allows them not, that they wouldn't be doing the testing if they didn't have the asset with them. So we have, for example, a couple small telecommunication companies that have just one. So I'll give you an example of one. If you go up to industries and you go up to the telecom industry, you'll see that someone like a Telmex would have many, where a Volcano Telecom, and you could watch a little video here, they would have 1 to 2 analyzers, I believe, for testing a section in the Sierra Nevada mountains, where they do have quite a few strings for their or small batteries for their cable stations, but they only have one large flooded system for their dial tone. So it really depends on your geographic location, how many operators, how you want to handle it. The larger ones tend to put it in the hand of each of their service guys, where a smaller telecom like this might just have 1 or 2.
Okay, great. Thank you again, Kurt. That concludes our time for today. As we said, you'll be receiving a follow-up email with the slides and a link to the recorded webinar. If you do have further questions and would like to find out more about what was talked about today, you can contact us at 800-828-1470 or visit us on the web at transcat.com. We do want to thank you for joining us today. We hope you found this informative, and we hope that you have a great rest of your week. Thank you very much.
Thank you, everyone.